So the first thing you are going to have to do on this quiz is just simplify radicals. You want to pay attention to two things here. You want to pay attention to what your index is and then what your exponents are once you take them out of the root. So anytime you have an even index, you need to be looking for, am I taking an odd exponent out? Because that's when this absolute value sign is going to be an issue. So like square root, if I have a square root, I have to be looking for, am I going to use absolute value signs? Cubed root, I'll never have to use an absolute value sign for a cubed root because I can have a negative inside a cube. I cannot have a negative inside a square root. Okay, so even roots are the only ones you have to worry about absolute value signs for. Odd roots, you don't need them. Okay? So if you need to make a note, even root, and you take out an odd exponent on the outside, that is going to require an absolute value. That's where that's going to happen. So let's look at this first one. This is the square root. If you do not see an index, it's anything that pairs up in twos. So I am going to just do my factor tree here. It's going to be lots of twos, by the way. So remember, when you're doing this, you're going to group them by that index. So in this case, it's going to be groups of 2. So I have 1, 2 that come out, another 2 that can come out. And by the way, as soon as you get to a perfect square, and I'll show you that in a second, you can stop there and actually use your square. And 1, 2 is going to stay in. Then I'm going to look at my variables. My A, I only have 1. So none of my A's can come out. For my B, I'm going to take that B, it's to the second power, divide by your index. So I have 1 B that will come out, and my remainder of 0 B's will stay in. So 1 B come out, no of my B's will stay in, so B is out here. And then I have to remember that I have a -4 here. So then I'm going to say, okay, did I take anything out that had an exponent of 1, any variable? Yes, I did. That's where that absolute value would come to play, is that B. Anything that's left on the outside, you're just going to multiply. So on the outside, I have 4 times 4 times 4, basically. So I have -64 on the outside. I have this absolute value of B on the outside, and I have 2A on the inside. All right? Just to show you what I mean by that factor tree. So 512 here, if I were to do my factor tree again, right here, you may recognize this as a perfect square, right? 256 is a perfect square. What is your perfect square of 256? Any takers? Yeah. So if you recognize 256 as a perfect square, you could say 16 and 16, and you could actually stop there. Or you could keep going. Hopefully you recognize 64 as a perfect square, right? 8 and 8. So you can do 8 and 8, and you can actually stop, and you can say, all right, I'm going to take an 8 out. And I'm going to take a 2 out, right? So if you recognize a perfect square within your factor tree, you can go ahead and do that perfect square and stop and take that out when it is a square root, all right? You could do the same thing with a cubed root. Those are not as easy to recognize as square roots, okay? So you can go all the way down your factor tree if you're more comfortable doing that. Or if it's a square root and you recognize a perfect square within your root, you can put those 2 factors there and stop, and you can take that whole group out, okay? So whichever is easier for you, you're going to get the same answer both ways. So this next one, you need to pay attention to the fact that I am not doing groups of 2 anymore. I am doing groups of 3. This does mean, however, you don't have to worry about absolute values at all because it's a cubed root. It doesn't matter if it's negative. So I'm going to do this again with my factor tree. I'm going to use a 5 because I know that's a prime for this guy. All right. So now I'm looking for groups of 3. This comes in a group of 3. I already have a 4 on the outside. So I have a 4 on the outside. I now have a 3 on the outside. And for my numbers, I know that 5 is going to stay on the inside. Make sure when you write your radical, you write that index, because I do count off for that. It's not the square root of that, it's the cubed root. So make sure that in your answer, you include the original index there. Let's look at the numbers. I'm going to start with my m. M to the 8. I am now going to divide that by 3. 8 divided by 3, well, that is 2, with a remainder of 2. So that means 2 m's will come out, and 2 m's will stay in. And then I'm going to do the same thing with my n. N to the 7th divided by 3. So 3 goes into 7 2 times with a remainder of 1. So 2 n's will also come out. 1 n will stay in. And then I'm going to simplify. On the outside, I have 4 times 3, 12, and then m squared n squared. It is the cubed root of 5 m squared n. And that is my answer there. So in order to add and subtract, they have to be like roots. That has 2 requirements. The first requirement is that the index be the same. The second requirement is that the radicand, the number on the inside, will be the same. Okay? So if you have one like this, then you can go ahead and add those together because you know they are alike. You will need to simplify eventually because 8 can be simplified. And then you want to check and make sure that then you can't add it to the other guy that you still had there. So for the first thing I could do, I could say, well, I know that these are alike. All right. And so if I know they're alike, I can just add or subtract their coefficients. 2 minus 2. How many square root of 8s do I have? Minus 2. 2 minus 2. Yeah, I have 0. So these actually zero out. That is my answer right there. Okay. 0 times the square root is still 0. So if it has, you're never going to write this. Never going to write that. That is just 0. So you have 2 square root of 3 plus 0. Okay, that's 2 square root of 3. Look at the next one. The next one appears to not have anything alike. This guy is an index of 3. This is as simple as this piece of it can get. So I actually am not going to do anything to that piece at all. These have the same index, but they don't have the same on the inside. So for this one, I need to simplify them and see if they will be alike. So you never want to leave it like this since they can be simplified. So this is definitely going to be part of my final answer because it is simple and it will not combine with anything. These I need to simplify and see what I can do. So I have a plus 3 times whatever I'm going to take out of it, which is 2. 5 is going to stay in. And then here I have a minus 3. And then I'm going to do my factor tree. Whatever comes out is going to be multiplied by that 3. Whatever stays in is there. I still actually don't have like terms. So when it says simplify, you may be adding and subtracting like we did up here, or you may just be simplifying your radicals. And so the final answer here is actually going to just be those 3 terms simplified. Multiply what's outside. All right. I cannot simplify that anymore. I can't add and subtract these 6s like I did these 2s because my radicand, my 5 and 2 are different. So this is actually as simple as this can get. Had these both been 2s, then I could add or subtract them. But because they're different, that's as simple as this one gets. All right, for multiplication, it does not matter if the radicands are the same as long as your index is the same here. So I can just distribute like I would, and I'm just going to multiply what's inside. So I'm going to say square root of 6 times square root of 2. That's the square root of 6 times 2. Minus square root of 6 times 3 square root of 6. 3 is on the outside, and I have 6 times 6 on the inside. So you multiply your outsides and you multiply your insides. The 6 and the 2 were both inside, you multiply them. The 3 was on the outside, that was technically a 1. 6 and 6 were on the inside, you multiply those. You can simplify these roots. So had I gone ahead and done 12, I could do my factor tree. So if I had simplified it like this and said square root of 12 minus 3 square root of 36, that simplifies, right? Or you may recognize square root of 6 times square root of 6 will always be just 6. Either way. Or you could simplify from here if you want to. 3, 2, and 2. And then, of course, you have 2 6s already. However you want to simplify these, you can. All right? You can go ahead and multiply them, or you can recognize it up front. Either way, you want to make sure that you take out anything that pairs up, leave in anything that does not. If you have 2 things on the outside, you need to make sure you multiply those. So this one looks like this. It simplifies to 2 square root of 3 minus 18. All right? You're multiplying the insides and multiplying the outsides. You cannot multiply outside to inside. All right? If you multiply a square root by itself, it ends up being just the number that was on the inside. You'll notice the square root of 6 times the square root of 6 simplified to just 6, right? Square root of 6 times square root of 2 is the square root of 12, which also simplifies. All right? So let's look at this next one. We're going to do it a little bit faster because we now think about the concept. Square root of 2 times the square root of 2. What is that going to be?
Just 2.
Just 2. But square root of 2 times 2 will have a 2 on the outside and a 2 on the inside. All right? Because I couldn't multiply those. They were outside to inside. Negative 5 times the square root of 2 is just negative 5 square root of 2. And then negative 5 times 2 is negative 10. So I'm going to look at this and say, can I simplify this anymore? Well, yeah, I can actually. I have basic integers here. 2 minus 10 is negative 8. And I have like terms here. My square root is the same index, obviously square, and then my radicand is both 2. So I can say 2 minus 5. That'll give me a negative 3 square root of 2. And now that is as simple as it gets. The first thing we did is we did just basic monomial over monomial. By that I mean you have one term over one term, no addition or subtraction thrown in there. All right? And so for this, you can simplify the outsides. Let's say 3 and 4 simplified. You can simplify those. You can simplify the insides. Now, anytime you have this negative, you want to go ahead and take that out. And so you want to go ahead and take that negative out of your radical. And now I can reduce the insides. Do 2 and 18 reduce? Well, yeah, they do. They're both divisible by 2. So I can reduce the 2 and the 18. 2 divided by 2 gives me a 1. K squared up here. 18 divided by 2 gives me a 9. K down there. All right? Now, neither one of those simplify. I can, however, simplify. What else do you think can reduce here inside my radicals? What else inside the radicals can reduce? My variables can, can't they? Yeah? So I can actually take 1k out of each of those. I can take a k out here and a k out here. So now I have 3 cubed root of k over 4i cubed root of 9. All right? 9 does not have a cubed root. It has a square root, but not a cubed root. Okay? So there's a couple ways to think about this particular one. You could multiply by 2 9s, right? but 9 is not really in its prime form. Does that make sense? So when I'm doing this one, I'm going to think about this 9 like this. I'm going to say, well, another way to write 9, you want it in primes. All right, get it in primes. 3 times 3. If I need to get rid of a cubed root, how many of those do I have to have? Like if it was a square root, I would just need 2 of them to get rid of it. Square root of 2 times square root of 2 gets rid of my root. This is cubed root. How many 3's do I have to get rid of a cubed root? I need 3 of them, right? And so I can actually multiply the top and bottom by just the cubed root of 3. All right? You don't have to multiply by 9 and 9 because 9 already has a pair in it. It only needs one more of those. So before you start deciding how to get rid of your radical, write it in primes. It will help you to not have as large of numbers. If you did it with 9s, you're going to have a much bigger number, and then you're going to have to reduce it out at the top, okay? So then on the top, I still have this 3 on the outside. Now on the inside, I have a k and a 3. That is cubed root, all right? On the bottom, now I've gotten rid of my radical. So I have the 4i right here, right? But I have the cubed root of 3 times 3 times 3. So what does that do to my 3? It just takes it out of my root altogether, right? If I have a group of 3, I can take it out of an index of 3. So I just have that 3 without the radical at all. That was my goal, was to get rid of that, okay? That was my goal. So now what do you think I can reduce? Outside to outside, these can cancel, right? 3 over 3. So I've reduced it to this right here. Is there anything else that I'm missing that I need to simplify? Yeah, remember we don't want radicals in the denominator. We don't want an I in the denominator. Well, how do I get rid of an I? I can just multiply it by an I. What is that? What happens? Well, if I have I times I down here, what does it change it to? I squared. So if I multiply it by I on the bottom, I have to multiply by an I on the top, right? So on the top, I have that I cubed root of 3k. What is 4i squared? It's just negative 4. That's actually my answer right there. So your goal is to reduce it as much as possible before you ever start. Pull that I out, and then reduce your 2 and your 18, your k squared and your k, right? And that's how we got to here. We reduced our 2 over 18, 1 over 9, k squared over k. That left a k squared in the top, and we pulled our negative out. There's our I. When you're looking at these, square roots are easy. To get rid of a square root, you just multiply it one time by itself. But cubed root, you have to have a set of 3 to get it out. You already had 2 3's. You just need to multiply. So get these in prime when it's higher than a square root. Get them in your prime, okay? 3 and 3 is what we had. We needed one more 3. That's how we got rid of that. That left us with 3k on top. And we were able to reduce that 3 and 3 that was left on bottom. And then we simplified our I. We put that I in the top by multiplying the top and bottom by I. What happens when you have a plus or minus? I can't just multiply by the square root of 5. That causes a problem because I have that 4 there. So we're using the term conjugate. Remember, conjugate is the same 2 terms. You just change the middle sign. So for this one right here, I'm going to use the 4 and the 5 square root of 5. But instead of a minus in there, I'm going to use a plus. And I'm going to do that to the top and to the bottom. All right. On the top, I'm just going to distribute 4 times 4. That gives me 16. And then 4 times 5 square root of 5 gives me 20 square root of 5. On the bottom, anytime you multiply conjugates, remember this little shortcut here. Anytime you multiply conjugates, you can just take the first one squared. Well, that is just 4 squared. Minus the second one squared. That is 5 square root of 5 squared. Let's talk about that bottom. Hopefully all of you can do 4 squared, right? This second piece is where I see the most issues, all right? This second piece is where I see the most issues. For this one, you're going to square the outside. What is 5 squared? Well, that's just 25. And that is going to be multiplied by, when you square a square root, you just have what's inside. So that 5 square root of 5 squared is 25 times 5. The outside squared times the radical being gone, what's left on the inside. And so you will be able to simplify this. This guy is 125, right? So we have 16 plus 20 square root of 5. We have gotten rid of our number in the our radical in the denominator. So we're going to say 125 minus 16 gives us negative 109. I will tell you, this is fine. I'll take that. I will tell you on your answer key, they just pulled the negative out of the denominator and put it in the numerator. So your answer key will show the negative 16 minus 20 square root of 5 over positive 109. Those are the same answers. They just pulled the negative out of the denominator and put it in the numerator. It's okay for me if you leave it in the denominator, if that's what happens. I will take it either way. This imaginary number is handled the same way. Remember, we're not going to leave an I in the denominator, but we have a plus or minus. So we're going to use the same concept. We're going to use conjugates. So I'm going to use the same 2 terms, but this was a minus, so this will be a plus. So you don't change the first term. Had that been negative 6, you would have left them alone, and you just change the inside. All right? We're going to FOIL the top. Negative 10 times 6 is negative 60. Negative 10 times 2i, negative 20i. 9i times 60. And then 9i times 2i. All right. On the bottom, it's going to do exactly the same. 6 squared, that's 36. Minus 2i squared, that's 4i squared. We have to square the 2 and the I. Some things that can simplify here. My I squareds, a positive 18i squared will become a negative 18. A negative 4i squared will become a positive 4. Your I squareds will just change your sign, which means I can now combine like terms. On the bottom here, I have a negative 60 and a negative 18. That's a negative 78. I have a negative 20i and a positive 54i. That is a positive 34i. On the bottom, I have 36 plus 4. That is 40. Now for your imaginaries, your answer key doesn't always do that. But what you want to do is you want to take the real, put it over that denominator, and the imaginary over that denominator, and then see if those fractions can reduce. They can. Both of these are divisible by 2. So that's going to give you negative 39 over 20. Plus, both of these are divisible by 2. That's going to give you 17 over 20i. That is your answer right there.